All right, Unit 7, Test Study Guide. So this unit was on exponential and logarithmic functions. Topic number 1, we are graphing, and this is just kind of a combination of both types of graphs. So describe first is exponential growth or decay. This one you don't really have to do anything except for look at the base. And the base is pretty easy to spot. Don't look for parentheses, that's a common misconception. Look for the exponent and then see what that exponent is attached to. So here's our exponent, it's attached to a 2/3. Because 2/3 is a value less than 1, that means that this is a decay. All right, same thing here, look for the x, look for the base. These two both happen to be in parentheses, but that's not always true. For instance, look at number 3. The base is 3, but it's not in parentheses, so don't use that as an indicator. Here for number 2, the base is 6/5, and since 6/5 is bigger than 1, that would be exponential growth. All right, for 3 and 4, we've got some exponential graphs. So what we want to do is start by figuring out what our parent function would be, and then we can figure out how you're going to shift those values. Okay, so our parent function would be just 3 to the x. Okay, so remember we want to set up, this is kind of our initial, and then you can take that and shift it. All right, so 3 raised to the -2, and these are all values that you could just sub right into your calculator. Okay, so 3 raised to the -2 power, you've got 1/9, or in fraction form, that is 0.1 repeating. 3 to the -1st is 1/3, or 0.3 repeating. 3 to the 0 is 1, 3 to the 1st is 3, and 3 to the 2nd is 9. So that's your parent function. And then what you do is you take a look at these transformations and see how it is that they're going to affect your graph. Okay, so now we want the new one. We'll set up an XY table. So this x plus 1, remember what that is doing is it is shifting your entire graph to the left. Okay, so you want to shift everything to the left 1 unit. So these 5 values are all going to get shifted to the left. Okay, and then this -6 means that all of your values are going to get shifted 6 units down. So you can take all of these values and then you would subtract 6 from them. So 0.1 repeating, if you subtract 6, you get -5.8 repeating. 0.3 repeating -6, and you would get -5.6 repeating. 1 minus 6 is -5. 3 minus 6 is -3. And 9 minus 6 is 3. So you've got those 5 values that you can plot on your graph. First thing you want to mark on is something called the horizontal asymptote, and you always use this value on the end. So you're going to go down 1, 2, 3, 4, 5, 6. And plot a dotted line for your horizontal asymptote, and then you can use that to start your graph. All right, so down 1, 2, 3, and then down just about to -6. All right, so -5.8. -2 is down at -5.6, so just a little bit higher. -1 is at -5. 0, -3, and then 1, +3. Okay, so the reason the dotted line is there is to make sure you don't go below it. So we should be, when we graph, just kind of skimming right along and then going up and through these points like that. So that's what the graph looks like. Our domain for every single exponential function is all reals, no matter what exponential function you're dealing with. And then the range is based on where that horizontal asymptote is. So this provides kind of like a boundary line for your graph. So the only y values you're going to use are y values that are above that line, which is at -6. You do not have the or equal to because it doesn't actually hit the line. All right, end behavior. So we have 2 ends of this graph. The right end right here, that's as x approaches infinity. You can see the arrows going up. So we say my function values go to +infinity. This one, left end right here, that is as x approaches -infinity. And here your graph is approaching that dotted line, and that dotted line has a value of -6. The y-intercept would be right here. It has an x-coordinate of 0, so you can even just look on the table, and you want to write that as an ordered pair. So x-coordinate and the matching y-coordinate would be -3. The asymptote is a y equals line because it's horizontal, and it's this dotted line which matches with this value right here, and that would be -6. All right, second one. This one right here, we can start with the parent function. The base here is 1/2. So our parent function is just 1/2 to the x. Okay, so 1/2 to the negative second is the same as 2 to the positive second, which would be 4. 1/2 to the negative first is the same as 2 to the first, which is 2. Anything to the 0 power is 1. 1/2 to the first is 1/2, or you could write 0.5. And 1/2 to the second is 1/4, or 0.25. So that's your initial. And then you want to make the transformations. So you can see what transformations we're going to have here. So starting with the x, so x minus 5 means your whole graph is going to shift 5 units to the right. So you can take all of these graphs and shift them to the right by 5 units, which counterintuitively means actually adding 5 to all of these values. And notice if you figure out the first one, they just go up by 1 each time with this exponential pattern. This +2 on the end means my whole graph is going to go up 2 units. So I can take all of these y values, and moving them up by 2 means adding 2 to each of these numbers. So 2 + 2, 1 + 2, 0.5 + 2, and 0.25 + 2. So very first thing we need to plot is our horizontal asymptote, which always matches this value right here. So we plot that as our dotted line. And then we're going to plot these 5 points. So 3, 6, it's right there. 4, 4, 5, 3, 6 and 2.5, and then 7 and 2.25. All right, so this is exponential decay. You can tell by the fact that the base is less than 1. So it's going to come down this way, and then on the right end, it'll be dragging along that dotted line, the horizontal asymptote. So all of our info over here. Domain for every exponential function is always all reals. Range is based on the value of the dotted line. So the only y values that are going to get hit are those y values that are above the dotted line, which has a value of 2. End behavior, as x approaches infinity, that's my right arrow. The right arrow is actually the one that's approaching the dotted line this time. And the dotted line has a value of 2. As x approaches negative infinity, that's the arrow on the left, and that arrow is going up. So we use positive infinity. Y-intercept, this one, we're going to have to do a little bit of work to figure out where, if at any point we have that y-intercept. So remember, with a y-intercept, what you do is you plug in 0 for x. So let's sub that in, do a little bit of side work here. So 1/2, and then when you sub in 0 for x, you get -5. And then +2. So that's something that you could sub into the calculator. So 1/2 raised to the -5th power, and then +2. So that comes out being 34. It's not something that you're going to see on the graph, but just so we know what the y-intercept is, when we sub in 0, we end up getting a y value of 34. So even though looking at the graph, it would seem like there isn't one, if you were to extend the graph, you would find it at 34. The asymptote is this dotted line. Since it's horizontal, it's a y equals, and the value that we get is 2. All right, with number 5 and number 6, we're going to move on to our log graphs. So these ones, remember, you're starting with basically the idea of what the parent exponential graph would be, and then you're switching x and y. So let's start off with our parent graph. And remember, like I just said, this is like the parent exponential graph, except you'd be switching x and y. So the values that you normally plug in for y are the ones that go in for x. So our base is 2. When you raise 2 to the -2nd power, that's 1/4, which is 0.25. When you raise 2 to the -1st power, you get 1/2, which is 1/2. When you raise 2 to the 0 power, you get 1. When you raise 2 to the 1st power, you get 2, and 2 to the 4th power, you get 4. So that's how you kind of reverse with the exponential. I'm sorry, this has been off the screen. You kind of reverse the exponential process to set up your base graph, and then it transforms to the new graph. So you can see we have one transformation right here. Since it's not in parentheses with the x, that means that's an up or down movement, and since it's -3, it's a downward movement. So there's no left or right movement. So since there's no left or right movement, our x values are actually going to just stay the exact same. And then the -3 is a y movement, and they move down. So you're going to take all of these and you're going to subtract 3. So -2 minus 3, -1 minus 3, 0 minus 3, 1 minus 3, and 2 minus 3. Okay, so we start with those points. First thing we need to plot on our graph, just like here we had a dotted horizontal line, with logarithmic you're going to have a dotted vertical line, and it's all based on what you see with the x. Here there are no parentheses, which means there's no left-right shift. If there's no left-right shift, then it's actually just right on this y-axis here. All right, so let's, based on that, plot these. So 0.25 is just a little bit over, and then down to -5, so just slightly off that graph right there. 0.5 is down at -4, so it'll be right around there, just a little farther to the right. 1 is at -3, 2 is at -2, and 4 is at -1. Okay, so you can use this dotted line, kind of just glide right along it till you hit these points, and then it starts this very slow growth off to the right, like that. So that's our logarithmic graph. Remember, since these are inverses of exponential, everything we knew about domain, range, end behavior, asymptotes, all that stuff completely swaps x for y. So this time, our domain is based on the dotted line, just like this range was based on the dotted line. So our domain is only the x values that are on the other side of the dotted line, and the dotted line has a value of 0. Okay, and then range this time is actually all reals. So remember, everything x and y related swapped. Domain was the x for exponential, so we do the y is now all reals since x's and y's traded. End behavior. Okay, so this one we kind of go opposite. This says the function goes up. So here the function goes up on this end. This would be the right end of the graph. So that is as x approaches infinity. And then the fill in the blank here is as the function goes down. The function goes down on this arrow, and this arrow isn't going all the way to the left. This arrow is just approaching the dotted line, and the dotted line has a value of 0. Okay, so that end behavior gets a little tricky for logs. X-intercept is where we cross the x-axis. So we're looking at this right here, and you can't actually see where it's going to cross, but we could add on an additional value if we wanted to. So remember, that would be setting y equal to 0. So we would take log base 2 of x minus 3 equals 0 and do a little side work for that. So I would add 3, so log base 2 of x is equal to 3, and since exponential form always makes more sense to us, let's convert it. So 2 is the base, 3 becomes the exponent, and that's equal to x. So that's 2 to the third is 8. So our x-intercept is 8, and we plugged in 0 for y in order to find it. All right, last piece is our asymptote. That's this dotted line right here. Since it's vertical, it's an x equals line, and that x value is 0. All right, so that's our first logarithmic graph. Let's take a look at the second one, number 6 on the next page. So we're doing something very similar here. We're starting by figuring out what the parent graph would be, and then working from there. So here the parent graph would be 1/3. Okay, so we can figure out x and y. So remember, we base this off of the parent exponential graph. All right, so these are the values we normally use for x in the exponential, so we use them for y in the logarithmic. So we are going to take this base and raise it to these exponents to figure out what goes in as x. So 1/3 to the -2nd is the same as 3 to the 2nd, which is 9. 1/3 to the -1st is the same as 3 to the 1st, which is 3. Anything to the 0 power is 1. 1/3 to the 1st power is 1/3, or in decimal form, that would be 0.3 repeating. 1/3 to the 2nd is 1/9, or again, in decimal form, would be 0.1 repeating. So that is your original parent graph, and then we want to make these transformations. You can see we've got 2, transformation right here, transformation right here. So with this first one, this x plus 2, you're going to take everything to the left 2 units. And then this +1 on the outside, you're going to take everyone up 1 unit. All right, so take this table. Let's make our transformations. So taking all of these values to the left 2 units means subtracting 2 from all the x values. So 9 minus 2, 3 minus 2, 1 minus 2. 0.3 minus 2, you end up with negative 1.6 repeating. And 0.1 repeating minus 2, you end up with negative 1.8 repeating. Okay, and then the y values are moving up 1, so you're going to take all these y values, you're going to add 1 to them. So negative 2 plus 1, negative 1 plus 1, 0 plus 1, 1 plus 1, 2 plus 1. So those values on the right are the ones that you're going to plot. Before that, you need a vertical asymptote. So since everything's shifting to the left 2 units, your vertical asymptote is going to shift to the left 2 units as well. So that's what we start with for our graph, and then plot the 5 points that you have. So 7, negative 1 would be 2, 4, 6, 7, down at negative 1. 1, 0 is right there. Negative 1, 1 would be right there. You can see we're getting closer to that dotted line. Negative 1.6 repeating is up at 2. And then negative 1.8 repeating is up at 3. So it's basically right on the line. Okay, so go right along this dotted line, connect through these points, and off to the right-hand side. Look like that. Okay, so this is logarithmic decay because the base is smaller than 1. All right, so let's write down all our info here. So the domain for log functions is based on where the vertical asymptote is. So the only x values we have on the graph are the ones on the other side of the dotted line, and the dotted line has a value of negative 2. So you could actually write that as the asymptote. So that dotted line has a value of negative 2. Next, our range is all reals for exponential functions. End behavior, you can see we have to figure out what these 2 pieces are. So the function goes up at this arrow right here, and it's going up as we approach the dotted line. All right, and the dotted line has a value of negative 2. And then the function goes down very slowly, this arrow right here, and that arrow is just going forever to the right. So that is infinity right there. Okay, x-intercept is a much easier one. You can see right there where it crosses through the x-axis. That ordered pair is 1, 0. You're looking for a point that has a y value of 0 right there. All right, so that is the last one for the graph. Let's move on to topic 2, logarithmic and exponential form. These ones are much quicker. So this is just converting back and forth between exponential form and logarithmic form. All right, so the first one's 8 to the second equals 64. So if you're converting into log form, it always starts with the word log. The base of the exponential becomes the base or the little subscript for the log. And then basically the other 2 numbers just trade places. So the 64 goes next and the 2 ends up on its own side. Okay, same thing here. So we start with the word log. The base of the exponential becomes the base for the log. The number on its own side tucks in with the log, and then the exponent ends up on its own on the right. Okay, number 9, start with the word log. The base here becomes the base there. Since 10 is the common log, you don't actually have to write it. You can if you want, but you don't have to. So I will write it just in case you forget. The 54 tucks into the log expression, and then the exponent goes on the right-hand side. And one last time, we've got log right here. This e right here becomes the base. The x minus 2 ends up on the inside, and I'm going to tuck it in parentheses just to make sure you don't lose any part of it. And then the exponent goes on its own. So for 9 and 10, I mentioned, remember, for number 9, 10 is the common log, so it's actually more likely you'll see it like this. And then number 10, log base e is the natural log, so it is more likely that you will see it like that. Okay, for 11 through 14, we're going back the other way. So exponential form. This 3 right here becomes the base. So not to be confused, it's this 3 that becomes the base and this 3 that becomes the exponent. And then the other number is by itself. So you're just reversing exactly what we did here. Okay, so this one, this little subscript, x becomes the base. This value on the other side becomes the exponent. And then the 7 goes on its own. Number 13, this subscript 4 becomes the base. This value on the other side is the exponent, and the value that was inside is on its own right here. And one last one. This one doesn't have a base written, but natural log, remember, is base e. And then the 38 is now its exponents equals that x. Okay, so the converting will come in handy when we move on to topic 3, which is evaluating logs. 2 different ways to do these. There's one that you can convert it into exponential form, and then if it's a known a known exponent of that value, then you just simplify it on your own. If you don't, then you would have to use the change of base formula. All right, so the change of base formula is this: common log of A divided by the common log of B. All right, so this one, you figure out 9 is the base. We do not know the exponent. It's supposed to come out to equal 81. So in this case, the exponent that's missing would be 2, because 9 to the second would give you 81. Number 16, 81 is the base. We do not know the exponent. It's supposed to come out to be 3. We talked about any time that it gets smaller, that must be a fraction, because fractions act like roots. So it's like what root of 81 would give us 3, and that would be the 4th root of 81. So the exponent would be a 1/4. Okay, another one like this. 5 is our base. We do not know the exponent, but my answer is supposed to be 1/25. With this pattern, a fraction only comes from negative exponents. So we know for sure that our missing exponent is negative. And then 5 to what power gives you 25? And that would be the second. So since it flips, it's negative. And then the second power is what gives you the 25. Okay, this one, 6 is our base. We do not know the exponent. It's supposed to come out to equal 1. This is a pretty easy pattern. Anytime that it comes out equal to 1, remember your missing exponent is just a 0, because anything to the 0 power gives you 1. All right, these next ones. This is 10 to some power gives us 63. 63 is not a power of 10. So this is where you would use the change of base formula. So common log of 63 is actually not one that you would have to do any work for. Common log of 63 is just, you have a common log button on the calculator, so you don't have to worry about doing the common log formula. I'm just going to pull up the Desmos calculator so I can show you guys. Okay, so our functions, you've got the common log under miscellaneous, so you do the common log of 63. And for these ones, you've been doing 4 decimals, so 1.7993. Okay, next one, log base 7 of 95. So our common log of 95 over the common log of 7. I'll mention this again. I've mentioned it before. Even if you have a fancier calculator that can do different log bases, I still want you to know this formula because you should be able to find it no matter what calculator you're using. So let's do this. So we're going to do common log of 95 divided by the common log of 7. All right, so 4 decimal places is a 2.3402. Sorry, it's sneaking into the next one. Same exact formula here. There's no exponent of 2 that gives you 78. So you do common log of 78 divided by common log of 2. And we can sub that in. So I'll replace the 95 with 78 and replace the, sorry, it's just not responding. There we go. Replace the 7 with a 2. Okay, so this, remember what this is saying is what exponent of 2 would give us 78. So this is telling us the exponent is 6.2854. Which should make sense because 2 to the 6th is 64 and 78 is bigger than 64 but not as big as the next exponent. All right, this one, natural log of 42. There is a natural log button on all calculators. So with that one, we could go, there's an ln right there, and we've got 42. So 3.7377, that 6 would round up. All right, so we've got some practice down evaluating those logarithms. The next topic on the next page is using our properties of logarithms. So we're going to copy them all down right here so that we'll be able to use them and reference them in the problems below. So our product rule, if you have a product on the inside it says that you can split that product up into two separate logs with addition in the middle. Quotient rule says if you have one log with a quotient on the inside, you can split them up into two separate logs with subtraction between them. And this last one says if you have a log with an exponent on the inside, you can take that exponent and move it out front of the log expression like it's a coefficient. Okay, so in this section, these 6 problems, we're going to be using those properties to either condense or expand each expression. So for 23, 24, 25, you're going to be condensing them so that there's nothing out front, no coefficients, and there's just one log. So first thing you need to do when you're condensing is take care of this property. All right, so if there's any values out front. So this 3, for instance, needs to move inside as an exponent. All right, so we start with log of 2 to the 3rd, so that 3 moves in as an exponent. And then we have addition, so it's this property right here. This says that you can take these 2 pieces and multiply them on the inside. So we have log of, on the inside, 2 to the 3rd times x minus 4. So 2 to the 3rd is 8, and we can distribute that 8 to the x minus 4. So that is the simplified expression for number 23. All right, number 24, just like I mentioned with this one, with 23, any values out front need to move inside first. So this 1/2 needs to move inside as an exponent. So we have log base 5 of 324 raised to the 1/2 power. And remember, the 1/2 power does not cut things in half. The 1/2 power is the same as a square root. All right, so 324 raised to the 1/2 power. That's the square root of 324. And that's one that we had in our last chapter. Square root of 324 is 18. Okay, and then this matches up with this property right here. This property says these 2 separate inside pieces can be written on the inside as a quotient. All right, so I can take the 18 and divide it by 2. So that 18 divided by 2 would come out to be 9, and that is condensed into one expression. Let's do one last condensing example with 25. So here the 3 can move in as an exponent. So I have natural log of 6 to the 3rd minus, and then here the 3/2 can move in as an exponent like that. So let's simplify these numbers first. So 6 to the 3rd is 6 times 6 times 6. That should be a known triple. That's 216 minus the 3/2 power is a little bit trickier. 4 cubed is 64, and then the square root of that is 8. So 4 to the 3/2 ends up being 8. And then just like we did with this one, your next property says that the 216 can be divided by 8. That's this quotient rule right here. And so 216 divided by 8 comes out to be 27. Okay, so those are the condensing ones. 26, 27, 28, we're just going to fully reverse that process and we're going to expand them. So this one, I would first actually simplify those exponents. So we have log base 3. I would take that 3 and expand. So when I when I cube x squared, I get x to the 6th. And when I cube y to the 5th, I get y to the 15th. So it's not a bad idea to do that first, and then you can expand all these properties. So I technically have a product on the inside, so I'm going to use this property right here to expand them with addition in the middle. So it expands them like this with addition in the middle. And then next property is each of these have an exponent, just like this rule right here, so that exponent can move out front as a coefficient. So this exponent of 6 will move out front as a coefficient, plus, and then this exponent of 15 will move out front as a coefficient. So these ones, you know they're fully expanded when the only thing on the inside of the log is either a single number or a single variable, no exponents, no products, no quotients. All right, it's 27. Again, let's simplify that exponent. So 2 to the 4th is 16. A cubed to the 4th would be a to the 12th. All right, so we can expand that way. So first thing, you've got a quotient on the inside, so I'm going to follow this property. Split them up as 2 separate logs with subtraction in the middle. So common log of 16 minus, natural log of a to the 12th. And then the other thing to do here is take care of this exponent using this rule. The exponent can come out front as a coefficient. So note, it does not come out front of everything. It just goes out front of where the exponent is attached to. Okay, one more of these. So this one I have a square roots. And so it would probably be a good idea to extend that. So remember, a square root is like the same as raising to the 1/2 power. So this is log base 4. When I raise this to the 1/2 power, I get p to the 3/2. And then q to the 10th raised to the 1/2 power ends up being q to the 5th. Because remember, you just multiply exponent by exponent. So this is a product. We'll use this rule right here. And expands the log by putting addition in the middle, like this. And then my exponents can come out front according to the power rule. So here the 3/2 comes out front of log base 4 of p plus, and then here the 5 comes out front of log base 4 of q. So remember my rule, your inside should just be a single variable or a single number. That's how you know that this process is completely done. All right, so topic number 5, logarithmic equations. We have a couple different types. Remember, you have log equals log and you have log equals number. So you can see these ones on this front page are log equals log, so that's one method that we'll be using. If you have log equals log, you want to make sure that you've used any properties to simplify them completely so that all you have on each side is just a single log. So 29 is ready to go. Once that's ready to go, you use that property that says that you can set the inside pieces equal to each other, but you can only do that once you're actually completely simplified on each side. Then you do a multi-step equation. So I'm going to subtract the 2x from both sides. So 5x minus 2x is 3x. And then I'm going to subtract the 7 from both sides. So 31 minus 7 leaves us with 24. Okay, and then divide both sides of the equation by 3. So 24 divided by 3 is 8. With logarithms, you always have to double check for extraneous solutions. The inside expression cannot be negative. So if I sub in 8, 5 times 8 plus 7 is positive, so that's good. 2 times 8 plus 31 is positive, so that's good. So this answer checks out. Number 30, again, simplify each side separately. Make sure there's only one log, which there is. Then once that is set up, you have that property that says that you can set those insides equal to each other, and then we would solve that equation. This equation is a quadratic. Quadratics are solved differently than linears are, like number 29. Quadratics, you have to get everything on one side of the equation. So I have my p squared on this side. I'm going to subtract 6p from both sides. So negative p minus 6p is negative 7p. And then I will subtract the 18 from both sides as well, leaving me with nothing on the right, which is my goal since it's a quadratic. All right, so always attempt factoring first when you're dealing with a quadratic. So p squared, you do p times p. And then these missing pieces are supposed to multiply to a negative 18, and my inside term is supposed to be a negative 7 when I combine them. So that'd be a negative 9 and a positive 2. All right, so that's how it factors. Take each one of these factors and set them equal to 0. So when I set p minus 9 equal to 0, I add 9 to both sides, and I get p equals 9. And when I take p plus 2 and set that equal to 0, I subtract 2 from both sides, and I end up with p equals negative 2. So I'm going to check them both for being extraneous, make sure the inside expressions are both positive. So 9 squared minus 9 is positive. 6 times 9 plus 18, also positive. Let's check the negative 2. Negative 2 squared is 4 minus negative 2. That would be a 6. So here, 6 times negative 2 is negative 12 plus 18 would be a positive 6. So remember, it's not whether this actual number is negative, it's whether it makes this expression negative when you sub it back in. So this one's totally fine. 31. All right, so this one, you've got some properties to take care of on the left-hand side before you can set the two pieces equal to each other. So you're practicing just like we were doing with 23, 24, 25. So on the left-hand side, very first thing you want to do is move that 1/2 in as an exponent. And then we'll also have to do the product property on the left-hand side. Okay, so this 36 to the 1/2 is 6, because remember, that's a square root. The 1/2 is the square root. So this is 6. And then my product property says I'm multiplying the inside of this times the inside of this. That's what I have right here. And now that that's done and I just have a single log on each side, that's when I can use the property that says I just set the two sides equal to each other. Okay, so when I set this equal to this, I'm also going to distribute this 6. So I have 18k plus 42 is equal to 132. All right, so I'm going to subtract 42 from both sides. So I have just 18k on the left. 32 minus 42 is 90. And then divide both sides of that equation by 18. So 90 divided by 18 is 5. And just check, so there's only one place where this would need to be subbed in. 3 times 5 plus 7 is positive. So that is not extraneous. All right, 32, I've got another one of these, another log equals log, and this time the right-hand side and the left-hand side need to be simplified up a little bit. So I would take this 2, and I'm going to move it inside as an exponent. So I have the common log of y plus 5 to the second. On the right-hand side, this is a quotient rule. I have log minus log, so what I can do is make it 1 log where I take what's on the inside and write it as a quotient, like that. Okay, so now each side is simplified separately. This is when I use the property that tells me I can drop the logs and just set the insides equal to each other. So 20 divided by 5 is 4. So this one turns into a quadratic. The left-hand side is a perfect square trinomial. So to FOIL it out, I have y times y, and then 5y, and I double that. So if I double 5y, I get 10y, and I square the 5. That gives me 25. So this 4 will need to be subtracted because it's a quadratic, so I have to get everything on one side. So I subtract 4 from each side. 25 minus 4 is 21. And then since it's a quadratic, the first attempt I make is to factor. So factoring, I need to multiply to 21, and then my inside terms need to add to 10. So multiplying to 21 and adding to 10 would be 7 and 3. Okay, so set each one of these equal to 0. When I take y plus 7 and set it equal to 0, I get y equals -7. And when I take y plus 3 and set it equal to 0, I get y equals -3. All right, to check them each out for being extraneous. So this, if I plug in the -7 plus 5 comes out to be a -2, and I cannot have a negative value inside my log. So that's extraneous. Again, it's not because the 7 was negative, it's because when I plugged it in here, I got something negative. All right, so we can check this, the -3. -3 plus 5 is fine because it comes out to be a +2. So even though this is a negative number itself, it does not make the inside negative, so that one checks out. All right, next we've got 2 more of these on the next page, and these are the log equals number examples. So the log equals number, your technique is to, first of all, make sure it's simplified, any properties that you might have to use, but then you turn it into exponential form in order to solve. So there's nothing I need to simplify here on the left, so I convert to exponential. So the 2 here is my base, the 7 over here becomes my exponent, and that is set equal to the expression on the inside, the 9m plus 2. So 2 to the 7th power, that is 128. And then this is just a pretty straightforward equation. So subtract 2 from each side. So when I subtract 2, I get 126 equals 9m. And then I can divide both sides of the equation by 9. So 126 divided by 9 turns out to be 14. And just like the previous page, anytime logarithms are in question, make sure that you're not going to get something negative. So 9 times 14 plus 2, definitely not negative. So this answer is just fine. Number 5, there's a property we need to use first before we put it into exponential form. So this one, actually, rather than using a property, I'm going to isolate that by dividing both sides by 5. So you could move this in as an exponent, but it could get ugly quickly. So I'm going to divide both sides by 5. So that will isolate the natural log expression, and 15 divided by 5 is 3. So now the natural log is isolated, we can convert it into exponential form. Remember, natural log is actually log base e, so that becomes our base. This 3 becomes our exponent, and we set that equal to that expression on the inside. All right, so this e to the third power is a decimal. So I'm going to show you e raised to the third power. So the left-hand side is 20 point, let's go 0.855. Okay, and then even though it's a weird decimal, weird irrational number, the process is still the exact same. So when I add 1 to both sides, this is just 21.0855. And then dividing by 2 is probably something you would want to use your calculator for. So 21.0855 divided by 2. So that gives me this 10.542, we'll go 8. You can stick to 4 decimals. That is our value of A. And when you sub that in here, times 2 minus 1, definitely not going to be negative. So this answer checks out. All right, our next topic, solving exponential equations. So these are all combined in one. So we have a few different types. There were some where we could change the bases to get them to match. There were some where we couldn't, so we had to put them into log form. So let's check them out. Always check the bases to see if they can be broken down to a common base first. So 64, I was saying 35 and 64 together. For number 35, 64 can be written as a power of 4. So you start by doing that. Notice the two sides are completely simplified already, so you jump into getting them to have the same base. So 64 is 4 to the third, and then you still keep that exact same exponent on the outside. So it's initially set up like this. Use our properties of exponents. When an exponent is raised to an exponent, you multiply them. So you'll be distributing that 3 like that. And then at this step, only because I have a single exponential on each side and that exponential is the same. That's the important part, is that the exponential is the same. I can take those exponents, drop the bases, and just set them equal to each other. So I am going to subtract this 5x from both sides. So 3x minus 5x is negative 2x. And I'm going to subtract the 21 from both sides. So negative 3 minus 21 is a negative 24. Then divide both sides by negative 2. So negative 24 divided by negative 2 is 12. Exponentials, their domain is all reals, so there's no worry about extraneous solutions when you're dealing with exponential functions, just logs. All right, 36, 9 and 1/27 can be broken down to a common base of 3, so start there. So 9 is 3 squared. Oops, sorry, that's a W. And 1/27 is 3 to the negative third power. So we start by getting our common base, then use exponent properties. So power to a power, you multiply them. So distribute that 2 like that, and multiply these 2. That gives us a negative 6W. So just like I did with 35, now that our two sides have the same base, we can drop the base and set the exponents equal to each other. All right, so since there are no constants here, I'll just subtract the 2W over here to the right. So I have negative 16. Negative 6W minus 2W would be a negative 8W. And to solve, I would divide both sides by 8. So negative 16 divided by negative 8 is positive 2. And again, no fear of extraneous solutions when you're dealing with exponential functions because the domain is all reals. All right, 37. This one, notice that 48 cannot be written as a power of 8. Don't confuse multiples with powers. 48 is a multiple of 8, but it's not a power of 8. So what we do in this situation is we turn it into logarithmic form to solve. So start with the word log. 8 becomes the base. 48 goes on the inside here, and then the n minus 5 ends up on its own side. So these, anytime you have something like what we have on the left, you're going to use our change of base formula to get a nice, lovely decimal for this. And then we can solve our equation just like normal. It just so happens that we'll have a change of base, a rational answer there. Okay, so we have, do it on the graphing calculator this time. So we have the common log of 48 divided by the common log of 8. And we'll use this decimal, so 1.8617 equals n minus 5. And then all I need to do to get the n by itself is just add 5 to both sides. So when I add 5 to this, I get 6.8617. Okay, let's check out number 38. We've got some new properties that we need to use. First thing we talk about is how the exponential piece needs to be isolated, and with number 38, this is the first time that it hasn't been. So first thing we do is just get this all by itself. So I'm going to start by adding this 11 to both sides. So add the 11, so 61 plus 11 would be 72. Then you're going to divide both sides by this 2 right here. So when you divide the left-hand side by 2, it's gone. 72 divided by 2 is 36. So now 36 is not an exponent of 3. Again, don't confuse exponent with multiple. So we do what we did with number 37. So we do log. 3 becomes the base of 36. And then the 4y ends up on its own side. So I'm going to do change of base again to get a decimal for my left-hand side. So change of base formula looks like that. So I'll sub this in. So common log of 36 divided by common log of 3. So I get 3.2619 is equal to 4y. And then to get that y by itself, I would divide both sides of the equation by 4. Okay, so I get 0.8155. Okay, next one, number 39. This one, the exponential part is isolated already. It's log base e, which means it's going to turn into natural log. So normally we would start with the log and then write the base, just like here we did log base 8. But this we know is going to be log base e, so that is natural log. Then comes the 65, and the a plus 1 would be on its own side. So with this one, you don't need change of base, because every calculator does have a natural log button. So natural log of 65 gets us what we need on the left. So 4.1744 equals a plus 1. And then to get a by itself, all you would do is subtract 1 from both sides. So when I take this and subtract 1, the 4 becomes a 3, but the decimal part stays the same. Okay, one more of these, number 40. This one, just like 38, we had to get the exponential part by itself first. So very first thing to do would be to add this 7 to both sides. So when I take negative 34 and I add 7 to that, I will get negative 27. And then the next thing is to divide both sides by that negative 3. Okay, oops, that should be subtraction, sorry. That would have messed us up later. Negative 27 divided by negative 3 is a positive 9. And now this looks just like what I had with number 39. So I convert it, into logarithmic form. So log base e is the natural log. The 9 goes within the function there, and the 2m minus 5 is now on its other side. So just like before, natural log doesn't need any special conversion. Natural log has its own button. So this we do 2.1972 for my left-hand side equals 2m minus 5. So just a two-step process to solve for m. First thing I want to do is add 5 to both sides. So since this is a 2, this is now 7.1972 equals 2m. And then I would take that and divide by 2. Okay, so this is what I end up with for m. Okay, so those are all of the exponential equations. Next topic that we have are applications. So within our applications, we have a few formulas that we're going to be using. So we're going to copy those down, make sure you've got them. So exponential growth and decay are almost identical. So capital A for the amounts. You've got a little a, which is the initial amounts. In parentheses, you have 1 plus r, which is the rate. That should always be in a decimal form. And then raised to t, which is the time. Exponential decay is almost identical, except you subtract the rate. Okay, and compound interest has some similarities. This time we use p for the principal amount. And then our rate gets divided by n, how many times a year you compound interest. And then the exponent is now n times t, because n times t would be the total number of times that interest gets compounded. So that's our setup. we've got a handful of applications here that are going to be on these particular equations. So Sophie invested $5,000 into an account that will increase by value. Write a function to model this situation, then find the value of the investment. So unless they specifically mention compounding interest, like 43 is a very similar setup, except they mention compounding interest. If they don't mention compounding at all, it actually just goes with one of these equations. So the account should be growing. That's going to be the very first equation, exponential growth. So the amount, she invested $5,000, that's the initial amount, into an account that will increase by value 2.3%. So that would be 0.023 each year. Write a function to model this situation. So the function would still have a t in there. And then we use that function to find the value after 15 years. Okay, so write it in function form. We want to know what the value would be after 15 years. I can add that together, and then you sub in 15 for the time. So these would all just be plugged right into a calculator. Desmos, your phone even. Graphing calculator, of course. So we get this value. And when it's money, make sure you just round to 2 decimal places. So 7,032 and 42 cents. Okay, number 42, you've got a baseball card is valued at $200, has increased in values. That's going to be exponential growth. So write a function. So this time I'm going to write function notation. So it started at $200. It increased by 7%, so that would be 0.07 goes in for R. And then when you're writing a function, you just leave the T there. All right. So then we want to find the value of the card in 2016. So anytime you have a setup like this, you assume that the starting year is going to be your 0. So this would be however many years later. So 1980 to 2000 is 20. An additional 16 years, this would be t equals 36, because it's been 36 years since 1980. All right, so our setup, we want to plug 36 in. Here I can simplify and just make this 1.07. And then the 36 gets subbed in as the exponent. So this is very worthy card here. 2,284 and 79 cents. Okay, so that's our second one. 43, I mentioned this is now going to be a compound interest problem because they specifically mention the interest compounding. If they don't say that word or something very similar, then chances are it's just the regular exponential growth problem. So Miles invested $2,400, that's your P, into a retirement account that earns 1.8% interest, so R is 0.018, compounded bi-monthly. So twice a month, there are 12 months in a year. So bi-monthly would mean that your N would be 24, because that's how many times a month you're going to compound. Write a function. So let's start with our actual function. So we have the principal amount, 1 plus, so the rate is 0.018, divided by the number of compoundings, which is 24, and then the 24 times whatever the time t is. All right, so we can clean up that equation a little bit. We'll plug in the 25 for the 25 years. And there's no reason to simplify anything in parentheses because we're just plugging this whole thing into our calculator anyway. So this is now 24 times 25. So you can multiply those exponents right when I sub everything in. So exponent is 24 times 25. So this is the value that we get. 3,763, and then we go with 31 cents. Okay, one more of these. So Sarah took out a $30,000 loan, that's P, at 4% interest, so R is 0.04, to put a new pool if the interest is compounded quarterly. So compounded quarterly means N would be 4. So write a function. So start with the principal amount, 1 plus R, so 0.04, divided by n. Remember, compounded quarterly means that n would be 4. And then n times t would be your function. Okay, so that's just the function itself. And then how much will she have paid after 12 years? Okay, so that amount, we just want the interest. So that's going to change how we answer the question a little bit. So we want to know how much she's paid, and then that will bring the $30,000 into question as well. So here, if we plug in 4 times 12 years, let's get an actual amount for this, and then make sure that we simplify properly to answer the question. Okay, so we've got that. Oops, I typed this in incorrectly. Sorry, I had 1% instead of 4%. There we go. All right, so this is how much she's paid. So we have how much she's paid. Then you want to subtract the $30,000 that was the initial loan. All right, because this is like the actual payment amount, and you guys will find out soon enough that you actually pay a whole lot of interest compared to the actual value. So she's got the initial loan. When you subtract the $30,000 from that, you end up with $18,366.78. So this is how much she's paid after 12 years. This is all that the loan was, so this much would be her interest. All right, on to our very last topic, topic 8, which is about regression. So we had 2 different types of regression that you guys did. I have a variety of different, so I did Desmos in the homework video, so I am going to use a graphing calculator in this video. If you're planning on using Desmos, feel free to pop back over and look at that homework video, homework 11 from this unit. All right, so table below, we've got stock over the course of 5 years. So we have just different values that you could sub in here. Remember, when you're talking about years, it's just easiest to make one of these 0 and have it like a starting year, because otherwise your values get very, very large. So we have 0, 1, 2, 3, 4, and then we have these stock values over here. So they're claiming that these stock values are growing exponentially rather than linearly or something like that. So those are the values that you type in. So first thing we want is use an exponential model to write an equation, then we're going to estimate using this. So you're going to hit the menu key, and then there's a value for statistics, and then stat calculations. All the way down here, letter A is the exponential model. So you press that. It's going to ask you where your lists are. So the X values, are in list A. The Y values are in list B. And then go ahead and press enter. So the regression equation, the A times B to the X, you use these values right here. So A is 400.07 and B is 1.09. So we would have Y equals A is 400.07 times B, which is 1.09, and then our exponent X there. So that's the function itself. Estimate the value in 2025. So 2025 would be since 1998. It's been 27 years. So 27 years since we started this problem in 1998. So you would just want to sub that into your equation. Okay, and that can get typed right into the calculator, back on just a normal calculator page. Okay, so you've got about $4,098.75. So it definitely is growing pretty quickly. Okay, so that's the exponential regression for 45. For 46, we're going to do a logarithmic model. So I can go back in and get another list and spreadsheets page. I'm going to add these values for wind speed, and then mark in the wind chill. Okay, so highlight one of these, same menu, same statistics option, same stat calculations. This time we have to go down a little bit further in order to get the logarithmic. So that's just the one right underneath the exponential. So same options. The X's are in list A, the Y's are in list B, and it's going to give you everything we need. So this is the formula, a plus b times the natural log of x. So this is a, about 7.91, and b is about negative 6.41. We'll round that up. So our equation, we've got 7.91 for a plus negative, so I could have done subtraction there, 6.41 times the natural log of x. All right, so that's our logarithmic. And then it says find the appropriate wind speed that corresponds to a wind chill factor of negative 18. So these are actually my y values. So this is asking us to sub in this value for y, and then we'll end up solving for x. Okay, so I'm going to sub negative 18 in for y, and then I will end up solving for x. Okay, so what I would do is I would subtract the 7.91 from both sides. So I'm just going to walk you through what I'm doing. So negative 18 minus 7.91. Oops, sorry, I did something weird there. Minus 7.91. There we go. So I get negative 25.91 equals negative 6.41 times the natural log of x. So I need to get this natural log by itself, so I'm going to divide both sides by negative 6.41. And that will give me 4. I'll use a few more decimals on this left-hand side. That's the natural log of x. So to get this, remember what you would do is convert into exponential form to solve for x. So this is log base e. So I put e, use that number as the exponent, and that's what gets the x by itself. Okay, so let's take e and use that value, that last answer, as the exponent. So x is equal to 56.95. And you want to make sure you're including any units, so this would be in miles per hour. And that would make sense if you think of the correlation. Very fast would definitely make it a lower wind chill factor. All right, 47 and 48, we are looking for the best fit. And the best fit is based on those r and r squared correlation coefficients. So we've got a table here. We are going to type that table into the very same lists and spreadsheets that we've been using. So these are years. So we're going to make this year 0, and then it's 2 years later, 4 years later, 8 years later, and 11 years later. Make sure you're not just doing like 1, 2, 3, 4, 5. Make sure you're looking at the relationship. Oops. 0. Oh my gosh. Okay, and then 18. Okay, so we're going to take a look at some different relationships here. So I am going to do this. Stat calculations. We are going to start with a linear regression. So 3 for the linear regression. Your y list is still the b's. Okay, so I'm going to make just a note of all of these. So linear, if we see, you can use either r or r squared, just make sure that you do the same thing each time. So the r for this one, we'll use 0.9873. Okay, and then let's check the quadratic. So back to this data. Same menu, statistics, stat calculations. This time we're going to use the quadratic regression. And B is where our Y's are. Yes, overwrite the data, that's fine. So here, oh, the last one this one uses r squared only. Okay, so let's make sure that we have r squared for the linear. So r squared for the quadratic is 0.975. And then let's check the cubic. We can go back for the linear as well. Actually, we could just square that value and that will tell us what the r is. So let's do a little side note here. So this, if I take 0.9873 and square it, just so I have an r squared to compare to, so that is 0.9747. So you can see it makes it just the tiniest bit lower than the quadratic. All right, cubic. Let's go back in here. And we're going to do the same regression. This time we're going to do the cubic regression, which is 7. yes, overwrite the data. And you can see here that the r squared is 0.9797. Okay, so with this one, you've got the highest value with the cubic. So since the cubic is your highest value, you are just going to write down what that formula would be. Okay, so we're going to go with the cubic with this one. So you have all of your different lovely values. All right, so we have, so 0.03, that's your x cubed. Here's your x squared minus 0.52 x squared. Here's the x plus 6.26x, and that is your constant plus 16.90. All right, so there's your cubic function. It says estimates the number of seniors in 2020, so that would be years since 2004. So that'd be 16 years since 2004. All right, so we'd have a 16 to plug into all of these values. Okay, so that we could just use just a little scratch pad there. So we're gonna plug in the 16 to this whole function. Okay, so we get approximately 106.82, so let's round that up to 107. Okay, very last problem here, number 48. We've got a table. We're going to check cubic, quartic, or exponential. So let me pull up a new spreadsheet. Sorry, one second. Okay, sorry, we're malfunctioning here. There we go. Okay, so new spreadsheet. So this, once again, we'll start with 0. Since it's years, these ones actually do just go up by 1 each time. Okay, so 1, 6.2, 9.7. Okay, so we've got these values, and we are going to use these. Hold on one second. Okay, sorry, just checking something. So our stats, we are going to check the cubic first, number 7. Oops, I missed something on there. Forgot to put the little brackets after the B. Okay, don't forget your little brackets. Okay, so this one is our cubic. So we've got all these values here. The cubic, that looks very good. So we've got 0.9999 for the cubic. So this one, 0.99992, just in case we need to compare. The quartic, let's kind of fill them in on the same, like let's not refill the C and D so we can actually see the next one. Okay, so quartic, the Y list is B. Okay, so then we're going to start this in column E so we don't run over the last one. Okay, so here's this one, the quartic, and R squared comes out to be 1. All right, so that's going to be hard to beat. This quartic comes out to be exactly 1. Let's double check the exponential. So back over to this column. This time we're going to go for the exponential. The Y list is B. And we want everything to start. Let's see, we had C, D, E, F. Okay, so we'll start this one in G so we don't block over anything. Okay, and that's, oh yeah, that's much worse. So we have 0.75 for the exponential. All right, so we're definitely going with the quartic for this one. So I'm glad we didn't erase anything. So here's the quartic regression. We've got lots of pieces here, so I'm going to copy that down. All right, so our quartic function, we have negative 0.03 x to the fourth. Here's our x cubed plus 0.28 x cubed minus 1.47 x squared plus 6.43 x and plus 1. That one's easy. Okay, so that is our whole function. Then estimate the number of books sold in 2014. So 2014 would be 6 years since 2008. So we want f of 6. Okay, so I'm not gonna write every little piece down there again. I'm just gonna type everything in. So negative 0.03 times 6 to the fourth plus 0.28 times 6 to the third minus 1.47 times 6 squared plus 0.43 times 6 plus 1. Okay, so that's about 8.26. That is slightly concerning, but I guess that is what the model is showing. Quartics, remember, they kind of loop around. So this one seems to think that we are going to be turning around and going back down. That works. That is what the model told us. So we have 8.26. Remember, these are in thousands of dollars, so we have $8,260. So if it follows this quartic model, remember they have that sort of W shape, so at some point it is going to turn around and go back down because this is a negative quartic function. So it looks like we passed the point where it turns around and goes back down.